Hello there and welcome to the Year 9 revision video on circle theorems. Let's get straight stuck into it and have a look at the circle theorem rules that we need to know for the end of Year 9. So the first one is that an isosceles triangle is formed when you take two lines that are the radius and then connect them up with a third line along the circumference. Now we know that this is an isosceles triangle because this point here has been labelled with the symbol O. And O, whenever you see it in a circle theorem, will always be referring to the origin or the centre of the circle. If it was just at any other point, then it would not necessarily form an isosceles triangle, but it definitely will when you use a line from the centre of the circle to the circumference of the circle. Circumference is the outside of the circle, the perimeter. And this line here is going to be the same distance as this line here. The two lines are going to be the same distance because they're both the value of the radius. And that's the definition of a circle. It's the set of points that are equidistant from the centre, which means that the radius is always the same length. Now what do you get when you've got an isosceles triangle? You also get two angles that are the same value at the bottom or near the circumference of the circle as well. So that's a rule to do with angles inside a shape that involves a circle and a triangle, that you will always get these two angles here being the same. So if one's 40 over here, the other one is 40 over there. So we'll look at circle theorem number 2. Circle theorem number 2 is whenever you take a circle and then connect 4 points on the circumference of that circle together, it forms what's called a cyclic quadrilateral. Yes, it's obviously going to be a quadrilateral because it's got 4 points and 4 sides, but the special word of cyclic means that those 4 points will fit inside a circle, or on the circumference of a circle rather. Every quadrilateral will fit inside a circle, but specifically on the circumference of the circle will contain the corners of the circle of this quadrilateral. Now in particular, there's a set of rules to do with the angles in this quadrilateral. Yes, they'll add up to 360. Angles inside a quadrilateral always add up to 360. But specifically in a cyclic quadrilateral, the two opposite angles will add up to make 180. So in this diagram, A and B will add together to make 180. And so will X and Y. X and Y will add together to make 180 degrees as well. Let's move on to the third one. The third one is when you take, so this O here is again referring to the origin. So whenever you take a diameter, a line that goes from one side of the circle to the other through the origin is the diameter. So whenever you take a diameter and then create a triangle using that line with another point on the circumference, the angle that you make at the circumference is always a right angle. So the posh word here of subtending is introduced. An angle subtending the diameter. Now if this line is the diameter, what the word subtending means is coming off of the diameter. So read this as an angle coming off of the diameter is a right angle. So it's coming off at a right angle to a point that is also on the circumference. Okay, so the next circle theorem is what I refer to as the Bowtie theorem. You can see here that the diagram looks a little bit like a bow tie. Now the actual circle theorem that's involved here is to do with subtending chords. Now this line along the bottom here is referred to as a chord, and it's an angle that's coming off of this chord. Any angle that comes off of this chord, no matter where it goes to on the circumference, will have an equal sized angle at the point on the circumference. So these two angles up here are going to be equal. And it also works down the bottom as well, because you could just draw the chord in a different position, such as up here, and then you get two equal angles that are down the bottom here. And if you've got two equal angles down the bottom, then you've got x and y, then these two angles inside here are probably also going to be equal to each other as well. The circle theorem here is called angles subtending the same chord in the same segment are equal. Then moving on to the final circle theorem, it's called the Arrowhead Theorem. Well, it's not called the Arrowhead Theorem, I call it the Arrowhead Theorem. You can refer to it as the Arrowhead Theorem, but the actual theorem is called angle at centre is twice the angle at the circumference. And what that means is that you take this angle at the top of the arrowhead, double it, and you get the angle that's in kind of like the armpit of the arrowhead. Sometimes this circle theorem looks a bit like this. Sometimes it looks a bit weird and it looks a little bit like this, but you can imagine if you just pick up the point at the top and move it round, then you get exactly the same circle theorem, but it just doesn't look like an arrowhead anymore. That's why it's not called the Arrowhead Theorem, because sometimes it doesn't look like an arrowhead theorem, but it's the angle at the centre, angle at the circumference. When you double it, will give you the angle at the centre, and it definitely needs to be the centre. A clue that it is the centre is that it will have the letter O for origin, in the centre there. Okay, so attached in the description of the video is a link to about 15 questions for us just to have some practice on using these rules of circle theorems. Make sure you've paused the video and given these a good go. Come back to these circle theorem rules if you need to, and we're now going to go through the answers to these questions. You can also go through them one by one if you wish. So the first circle theorem is this one here. We've got a shape that looks like this, and the question is, find the size of angle PQS. And what that means is start at point P, then go to point Q, and then go to point S. And then the angle that's created as you've gone from P to Q to S is the angle that we're looking for in this question. Now in this question it looks like a little bow tie, so we're going to be using the bow tie theorem here. And it's going to be equal to either 34 or 41, and we just need to make a decision as to which one it is. Let's go back to this diagram here, and it looks like it's not equal to the angle that's it's in the same triangle as, it's equal to the angle where it's opposite the same chord as. So if I draw my chord down here, this is the chord in this question, then this angle 41 up here is going to be the same as the missing angle that we want to find up here. So the question mark PQS is equal to 41 degrees. And there we are, that's the answer to that question. Let's move on to the next one. Look, it's just like the Arrowhead Theorem here, but it's got one of those Arrowhead Theorem shapes where this top bit, the bit at the circumference, has been moved round the shape to a different point. So find the size of angle L to O to P. So this angle that's created when I go from L to O to P, well, you take the angle at the circumference, double it, and you get the angle at the centre. So angle LOP equals 2 times 48, which is 96. So 96 degrees is the answer. Let's move on to the next one. Quite a difficult one here. Calculate the size of angle AOB. So angle A to O to B, that would be this angle inside here. And, well, what do I need to use here? I've got 106 up here, I've got 57 down here. In fact, if I look at the shape from this point of view, from this arrowhead here, then I can see that it's the Arrowhead Theorem I need to use. So it's going to be 57 doubled to get to this angle here. So 2 times 57 will equal 114, and that's the answer to the question. We actually didn't need to use the answer of 106 in this one. Okay, moving on to the next one then. So work out the size of angle ODC. So ODC, O to D to C. Okay, so the first thing I need to think of is I need to work out this total angle in here. But I could split it up into two parts. I could split it up into this part here, we'll call this part X, and then maybe we might call this part here Y. And maybe that might help us in splitting up the angle. So the first thing I might do, I probably won't be able to go straight to this answer straight away, but what I might be able to do is go to a different angle first, and then work my way to either angle X or Y or both of them. I think the first thing I might try is by working out this angle here. This angle here is 150, and writing on the diagram is absolutely fine. Something else that might be helpful to me is noticing that I have an isosceles triangle here, ODB back to O. So that will mean that I've got two equal angles at the bottom here and here that are equal to each other. So that's going to be angles in a triangle add up to 180. I need to use that fact as well. So it's going to be 180 minus 150 is 30. So I've got 30 degrees left to divide between this angle up here and this angle down here. So 30 divided by 2 is 15. So this angle inside here is 15. This side here is an angle of 15 as well. What else is there to work out? Well, I've also got a quadrilateral that goes around the outside of the arrowhead. So round here, A, B, C, D will form a quadrilateral. And angles that are opposite in a quadrilateral will add up to 180. So the angle at A and the angle at C will add up to 180. So what is that going to be? That's going to be 105. So this angle here is 105. And then the last thing to work out will be to work out what x is. X will be whatever's left over from the triangle here. So that's going to be 180 minus 105. And then take away the 27 as well. So that will leave me with 75 in here. And then take away the 27. We'll take away the 7 first. I'm down to 68. And then that'll be 48. So angle x is 48. The total answer here, ODC, is going to be 15 add 48, which is going to give me 63 degrees. So there we are, that's the answer to this question here, which is work out ODC. Let's move on to the next one. So here we're working out the size of angle GFE. G to F to E. Our classic question where students go wrong here. And what they think is I've got a quadrilateral here, and angles in a quadrilateral, the opposite ones, add to make 180. Well, that's true, but only if all 4 points on the quadrilateral are on the circumference of the circle. So this point here being in the centre means that the circle theorem is not allowed to be used. What I have to do first in this question is to go up to this angle first up here. So the Arrowhead Theorem is going to come into play first. I need to half this angle to get this angle up here. So angle GDE is going to equal half of 98. 98 divided by 2, which will be 49. Now I can use the quadrilateral theorem where the opposite angles inside a quadrilateral add together to make 180. So angle GFE will equal 180 minus 49. Okay, well let's take away 50 and add on 1. 130, add on the 1 again. 131 degrees is your answer. So this angle here is 131. Okay, let's move on to the next one. So in this question, we're working out the size of angle P to S to R. So this angle up here. And in this question, the answer is going to be whatever's opposite to 78 when I look at these quadrilateral around the outside. So it's going to be 180, take away 78, which gives me 102 degrees. And there we are, that's the answer to this question. Let's move on to the next one. Part A is to write down the size of angle ACD. So it's A to C to D, so that's this angle inside here. Well, in this case, it's going to be a little bow tie theorem. Ignore the lines that are going to the centre, and you'll be able to see the bow tie. So that means that the angles that are coming off of this chord, the angle at B and the angle at C, must be equal to each other. So ACD equals 52. Then we've got write down the size of angle OAD, so that's the angle inside here, and that's the circle theorem where you've got an arrowhead and you need to double 52 to get this angle inside here. So angle OA, so AOD is 104 degrees. Let's Move on to the next one. Calculate the size of angle ADB. So what I think we need to do here is we need to recognise that ABD is a right angled triangle. We've got a right angle here because it's one of the circle theorems whereby if you've got the diameter of the circle, how do I know this is the diameter? Well, it's a line that goes from one side of the circle to the other, going through the centre of the circle. I know it's going through the centre of the circle because it has the letter O there, O for origin. So once you've got a diameter, any angle that subtends either side of that diameter to create a triangle at B is going to be a right angle at B. So how do I work out ADB, A to D to B, that's this angle here? Well, I've got 180 degrees in a triangle, I've got a right angle at the top, and I've got 58 degrees on the left, so that's going to be 32 degrees left over. So angle ADB is 32 degrees. And the next question, calculate the size of angle B to C to D, so that's this angle over here. Well, in this case, I need to look at it from a different point of view, not triangles this time, but quadrilaterals. And the opposite sides of a quadrilateral add up to 180 when they're inside a circle. So it's 180 minus 58, which is going to give me, we'll take away 60 and add 2, 122. And there we are, that's the answer to this question. Let's move on to the next one. Calculate the size of angle PQR, P to Q to R. Okay, well in this question here I can see I've got myself an isosceles triangle, POR, that's an isosceles triangle. So I've got this angle here, must be the same as this angle over here, because they've got equal angles at the bottom. Then I know that my angles inside a triangle will have to add up to 180. So I'm going to do 180 minus 36 minus 36. 36 minus 36 is 72, so I'll have 108 degrees left for this angle here. And then I need to half it to get to this angle here, our final answer. So 108 divided by 2 is 54 degrees. And that's the answer for this question. Moving on to the next one. Calculate the size of angle HKJ, H to K to J. So this angle inside here. Okay, well the first thing I'll probably be looking at is this angle over here. That's going to be opposite to this one here. So that's going to be 56 degrees. Once I know that that angle there is 56 degrees, I will be able to work out, oh, we've got KJ as the diameter, so we needed to actually read this question here. So if we know that's the diameter, then I know I've got a 90 degree angle here. Here we are, I've just cracked this question now. So H to K to J, so the reason we know this is a right angle here is because we know that this is the diameter line that goes through the centre. And then when you've got a triangle that subtends the diameter, that triangle is a right angled triangle at the point on the circumference. So now we've got a triangle here, HKJ, where we've got a right angle and a 58 degrees in it, so 56 degrees in it. So we'll work out what's left from 180, because you always get 180 degrees in a triangle. So that would be 90 minus 56, so that would be 34 degrees. So the answer to this question is 34 degrees. Okay, so let's move on to the next question, and what I can see immediately here is that I've got two little arrow symbols that are referring to parallel lines. So what that will mean is that I'll probably have an angle fact to do with parallel lines creep itself into this question, and I can immediately see that if I start at A, then go to B, then go to D, then go to C, A, B, D, C, then that will form a Z kind of shape. And there's a rule, there's an angle rule to do with your Year 7 knowledge of parallel line rules, that this angle here will be equal to this angle here. And that's before I've even got on to doing the question here. Calculate the size of angle BDC, so B to D to C. Okay, so we're working out this angle here. We've also got to make sure we read the question, because it does say that AB is a diameter. So that means that this will be the centre of the circle, and in which case I can immediately deduce that this will be a right angle triangle because it's either side of the diameter forming a triangle to point D, so there'll be a right angle at point D. Then I can work out that there will be a 20-degree angle up here, because angles inside a triangle will always add up to 180. And then from my alternate angle facts, this angle down here will also be 20 degrees, so BDC will equal 20 degrees. Let's move on to the next one. So we've got here that find the size of angle ABC, so angle ABC here. Now, in fact, if we just look at the outside of the circle, ABCD, we've got a quadrilateral here, and angles opposite each other inside a quadrilateral will add together to make 180, or a cyclic quadrilateral, add together to make 180. So this one will equal 180 minus 68, so that will be 112 degrees, because 112 add 68 will make 180. And find the size of angle AOC, so that will be this one here. Well, this one's the Arrowhead Theorem, ADCO, there's the arrowhead there, so you double this number to get to this angle inside here. 2 times 68, that will give you 120, 136 degrees. There we are. Let's move on to the next one. Calculate the size of angle EH, so EFH, E to F to H. Well, this one will be equal to 67, because if you draw a little chord at H to E, then you've got two angles coming off of HE, one at G, one at F, and those two angles will be the same. So 67 is your answer to the first bit. And then angle EDH, so that's this one down here, you can ignore this dotted line now, so let me just erase it. And now if you look on the outside of the circle, you've got GHDE, and that will be a circle theorem that will involve opposite angles inside a cyclic quadrilateral. These two angles will add together to make 180, so your answer is going to be 180 minus 67, and that would be 113 degrees. So 113 is your answer to the second part. Moving on to the next one, find the size of angle ADB, A to D to B. So if I draw the line B to D in, then that might help us a little bit. And then once I've drawn that, I've got the diameter here, so that will be a right angle there. The next thing I could probably do is I could work out this angle over here, because I've got a quadrilateral around the outside, and these two angles here will add together to make 180. So BAD, the angle B to A to D, will be 180 minus 112, and that will be 68 degrees. So 68 degrees will be this angle here. And the answer, A to D to B, will be this angle up here, and that will be whatever's left from 180 inside your triangle, which will be 12 degrees. So ADB equals 12 degrees. Moving on to the next one, a little proof of this circle theorem here. Definitely two proofs that you'll now need to know for year 9, this one and the next one coming up. Okay, so we need to prove that angle A to C to B is a right angle. So that we need to prove that this angle here is a right angle. And you must not use any circle theorems in your proof. Okay, so the first thing I'm going to do is I'm going to chop this triangle in half. So I've got an angle X here and an angle Y here. And angle X and angle Y are probably going to be different sized angles. Now, by the rule of triangles, this is going to be angle X and this is going to be angle Y. So I'm going to need to start writing some stuff down. So call angle ACO X and BCO Y. Then, by isosceles triangles, you do have to write all of this, because if you're proving something, you need a full explanation of why something is what it is, and you need to write sentences if you're going to provide a full explanation. Then by isosceles triangles, CAO equals x, that's the angle from C to A to O, that's also x, and this one down here, O to B to C, also equals y. Then, from angles in a triangle adding up to 180, this angle here is going to be 180 take away 2x. So then, by the sum of the angles in a triangle equaling 360, no, not 360, 180, we can infer that angle COA, the C to O to A, is 180 minus 2x. And the same on this side as well, 180 minus 2y. So that will be BOC equals 180 minus 2y. Now what we also know is that this line here is a straight line. So these two angles that are on the straight line must add up to 180. So by angles on a straight line sum to 180, we know that 180 minus 2x plus 180 minus 2y will equal 180 degrees. Now what we've got ourselves here is a little equation that we could simplify. I could take away 180 from both sides, and that will leave me with 180 minus 2x minus 2y equals 0. Let's now add 2x and add 2y onto both sides, and that will give me 180 equals 2x plus 2y. And then let's half everything, so divide by 2 on both sides. That will give me 90 equals x plus y. And therefore, if we then go back to the start, we have the angle x plus y was divided into 2, like it is here, where the addition of the 2 will equal 90 degrees. So therefore, ACB equals 90 degrees. And there we are, that's the proof and a full explanation as to why this angle up here is definitely always 90 degrees. And we'll move on to the final question, the final circle theorem proof. You only need to know 2 proofs. You need to know how to do a lot of questions. What we'll do first here is we'll divide this shape into 2, and we'll call this side x and this side y. Now what we want to do is to double x plus y and give us the angle down here. But we're not allowed to just jump straight to it, we have to prove it, we have to show that that is what happens. So same as last time, we'll call BAO the angle x, and we'll call CAO the angle y. Then from isosceles triangle, this is angle x and this is angle y. So by the rules of isosceles triangles, ABO equals x and ACO equals y. Now the angles inside the triangle here, so by the sum of angles in a triangle sum to 180, we know that angle BOA will equal 180 minus 2x, and COA will be 180 minus 2y. Then from the angles around a circle, so we're now doing angles around O, by the sum of angles around O equals 360. We know that if we call this angle capital, no, let's not use capital A, let's use angle Z down here, then Z is going to equal 360 minus 180 minus 2x, because that's what this angle here is, 180 minus 2x, and this angle here is 180 minus 2y. So it'd be minus 180 minus 2x, and then minus 180 minus 2y, but with brackets around them, because we're taking away all of this, and we're also taking away all of this. So z is going to equal 360, take away 180, but now we're taking away negative 2x, so that'll be add 2x, for the double negative, and then take away 180, and then it would be take away minus 2y, that would be a double negative, so that would be add 2y. Now let's simplify a little bit. We've got 360 and then minus 180 and then minus 180, and then all of that will just cancel each other out. So we're left with z equals 2x plus 2y, which is double x plus y. So therefore, always write yourself a nice little conclusion. Angle BOC is double angle BAC, which is x plus y up here, and this one here is 2 lots of x plus y. And there we are, we've shown it. We've proved that the angle at the top, if you double it, will give you the angle at the centre. So there we are, that's all the questions we're going to go through on the circle theorems. Hopefully that's a bit of a reminder of how the circle theorems work, how you can apply them in questions, and yeah, hopefully you found this video helpful. Thanks very much for watching.